Hello, welcome to my new video where I will discuss three very important topics on linear algebra. First, I will discuss about span of vectors. Now, what is span? In a two-dimensional case, span is the direction of the vector. If this is a vector A, then the span of this vector is, if we put a straight line which will of infinite length, this is the span of the vector. This is the span of a vector in a two-dimensional case, that is in R2. In R2 itself, we can draw the span of two vectors which have an angle between them. If this is two vector, say, let me clear this thing. Let me draw it again. In a two-dimensional case, the span, if we have to define the span of R2, the whole two-dimensional plane, then the span will be, we can say, to define the span will be, if this is the vector 1 0, that is the basis vector, and 0 1, the span is all the vectors which can be created with the linear combinations of these two basis vectors. So the span of these basis vectors is the whole R2 itself. Similarly, in a three-dimensional case, in R3, the span of it's okay, this would be 1 0 0, this would be 0 1 0, and this would be, through this would be 0 0 1. If this is x-axis, this is y-axis, and this is z-axis, then we can say all the possible infinite number of vectors that can be possibly made with the linear combinations of these three basis vectors in R3 is the span of those vectors will be the whole three-dimensional space. Now if we have to put in a two-dimensional case, say this is 1 1 vector, so the span of 1 1 vector would be same as the span of 2 2 vector. The span of 1 1 vector would be same as the span of -1 -1 vector, -1 -1 1 1 2 2. So all the vectors which have coordinates -n or n, all of these vectors have same span as 1 1, which is the straight line through it. This is the span. So similarly, for any vector which has y equals to 0, the span of those vectors will be the x-axis itself, that is the span of 1 0 vector. The span of 1 0 vector is the x-axis, the whole x-axis. The span of 0 0 1 vector, is the whole y-axis. So this is the main concept about span. Now we will go to the next topic, that is linear independence of vectors. Now what is linear independence of vectors? In a two-dimensional case, if we have an angle between two vectors which is not zero, then those two vectors are linearly independent. These two vectors are linearly independent, but these these two vectors, say if this vector is -2 -2 and this vector is say 3 3, then these two vectors are not linearly independent, because these two vectors has a these two vectors, one of these vectors is a scalar multiple of the other, or any vector that is created by any two vectors, say the resultant vector of these two, any vector can be created with these two vectors. Any vectors can be created with these two vectors. These two vectors are linearly independent, but all the infinite number of vectors that can be created with these two vectors are linearly dependent on these two. And as we have discussed about the span of all those vectors made with these, say the vector is a and b, with the vectors a and b, the span will be the whole R2. So the span of these two vectors a and b is whole R2, but the span of only these vector b is this straight line. The span of only this vector a is this straight line. But the span of a and b, if we have to discuss, then that will be whole R2. So any vector in two-dimensional case, any vector that have an angle which is not equals to 0 are linearly independent vector. Now let me clear this thing. Now mathematically we can write, or we can say algebraically we can write, if we have vectors, say we have n-dimensional vector, a set of n-dimensional vector which we can accommodate in a matrix, say the matrix is A. Sorry, let me write it clearly. If a matrix consists of a set of n-dimensional vectors, say the matrix is n cross n matrix, okay, and the vectors are a11, a21, up to an1. The next vector is, all the vectors are column vectors. The next vector is a12, a22 up to an2. a1n, a2n up to an. If this vector is, let me write in yellow, if this vector is v1, this vector is v2, this vector is v3. If we have to test the independent nature of these vectors, then we can write, if a1 v1 plus a2 v2, sorry, this would be n up to n vn is equal to 0, only when all the scalar multiples are 0 individually. That means this thing can be written in matrix vector multiplication form, which is, sorry, I have done this. This could be a problem here. I have mentioned a here and a here also. Let me write it as x. If these x's are variable, obviously variable, x1, x2, v2 plus up to xn vn is equal to 0, only when all these xi's are 0, then we can say that v1, v2, vn are linearly independent of each other. That means we can write x1, x2 up to xn is equal to 0. So we can write, if this is a vector x, we can write ax is equal to 0, which is a homogeneous equation, obviously. Homogeneous equation. So for a homogeneous equation, if the vector is a 0 vector, if the vector is a 0 vector, only then we can say that the column vectors of A matrix will be linearly independent of each other. And there is a term, if a n cross n matrix like this one, if a n cross n matrix have the same number of as the order of the matrix has same number of as n cross n matrix, if n cross n matrix has n number of linearly independent column vectors, then the rank of that matrix is equal to will be n. If it has n minus 1 number of linearly independent vector, then the rank will be n minus 1, and so on. I will discuss it with an example in the next video, and we will have next topic covered in the next video as well, which is the null space. I have already prepared the slides, so for now this much. If you have any question, we will obviously discuss with one or two examples in the next videos, so that if there is any doubt, that would be cleared. So for now, this is the end of the video. Thank you.